talking about PID controller. If you are trying to find C of t, it is essentially kp multiplied by the error signal plus ki p naught pt dt dp plus kp differentiation of error signal. So if we do Laplace transform, we're going to have like this. So in short, DS is going to be my input, and CS is going to be my output. US. U of S. And C of S is going to be U of S over U of S. This is something we talked about last time. And we have come up with the conclusion what the KP and KI is going to look like. So if we have high gain system, we are going to reduce steady state error, but our damping ratio becomes smaller and smaller. So can we eliminate the steady state error when we design a controller? This time we're going to talk about PD controller. So PD controller, essentially it is going to be U over error. That is going to take only this part and this part. So we're going to have KP plus KDS. So obviously this one is not realizable, which means this is improper. But mathematically, can we do a little bit analysis for this thing? That is something we're going to talk about today. So when we have this kind of things, I'm going to tell you what the advantage of this thing and prove that when we are dealing with example. The first advantage is that it's going to decrease damping ratio. Second advantage is it's going to decrease rise time. Okay, so it means that we can achieve steady settling time with smaller amount of duration, and meanwhile the overshoot can be taken care by PD controller. So that's the reason we always say that PD controller is the best controller we can ever build when we are dealing with PID controller. However, the biggest advantage of PD controller is what? This is improper, which means this thing cannot be implemented physically. So even though this has a lot of advantages, we cannot do it. But we can use this advantage, try to come up with something that make everything feasible or implementable. Okay, there are some remarks over here. I would suggest you guys read those kind of things when you go home. Okay, let's take a look at an example. So the problem statement is consider the closed loop structure of the second order system shown with a PD controller, which is over here in the figure. If Kp is 10, determine the steady state error and the system response of the systems for different KD. So for this kind of problem, it's easy for us to do the closed loop transfer function because, well, I believe you guys know how to deal with this thing since we have done this transfer function many times. It is going to be controller multiplied by plant over 1 plus CG. So if we put everything all together, the transfer function is going to be KDS plus KP. Over here is going to be S squared plus 1.8 plus KD S plus 1 plus KP. Okay? Nothing fancy, and everything has been discussed before we see this transfer function. So obviously, over here, this is what? Second order equation. So when this is the second order equation, okay, and this one over here, this is second order equation, which means it's going to be S squared plus 2 zeta omega ns plus omega n squared, right? So if we say Kp is a fixed number, which is 10 in this problem statement, right? You guys see the problem statement, you know Kp is 10. So clearly, omega n is going to be what? Square root of 11 radians per second. The question I have for you guys is the zeta going to be affected by Kp? Not at all, right? Because since we say Kp is a fixed number, which means the zeta is going to be determined by Kd. So if we want to have smaller zeta, what we can do is we can have smaller Kd. So if we can adjust this part over here, we certainly can change the damping ratio, which means we can take care of what? Overshoot. Okay? So that is telling us we can tune omega n by adjusting Kp. And you must do this step first, because this term over here is a couple term of zeta and omega n. So you cannot say, okay, I want to tune this part and determine this part. You cannot do that. We would like to tune this part because Kp can be determined by determining what is my omega n. So if you say, okay, I want to have my this part over here somewhere. Let's say I need to have some kind of speed, sailing time. Then we determine this part first. Then we can determine what's going on over here. Then we have our Kp. Once our Kp is determined, we know our damping ratio should have our overshoot less than 5%. Then this part can be determined as well. Okay? Then we continue zeta by adjusting So if we have a PD controller, we can adjust my speed. We can adjust my overshoot based on the configuration, which is pretty neat. But again, we cannot do that this one over here is improper, which means this is not physically implementable. And in your notes, you should be able to see what's going on. So if your KD you can see if your KD becomes different, what kind of overshoot you're going to have. However, when you are dealing with this kind of things, there is one other thing we cannot determine at all, which is you got a 0 over here. Sometimes the 0 is going to play some specific role in your system. So when you are dealing with those kind of things, be sure you know what you're dealing with. In this specific problem, I would suggest you guys go home and use MATLAB to do a simulation. You guys know how to use MATLAB to do a simulation? No? Okay, let's do a little bit about MATLAB before we move on, because I think some of those kind of things need to be used in the future homework. Okay, so for this specific configuration over here, you can say I'll have my KP equals to 10. Yeah, sorry. In the very beginning, when you are designing your MATLAB, be sure you clear up all the variables, which means the memory should be clean. So we use clear. This command over here is going to clear out all the variables in the memory. So your workspace is going to be no variable at all. Once that's done, you should have KP equals to 10. Right? And KD can be different number. It can be 0, it can be 1, it can be 10, it can be whatever. Then I have my C equals to TF. KP, KD, KP. Okay, or you can do 0, 1. It will be fine. The reason we're doing this one is because this is my numerator, and this one is my denominator, right? So it's going to be KD S plus KT over. This is my S term. This is my constant term. So it's going to be 0S plus 1. So it should be like this, because even though I omit that part, but the denominator over here is going to be what? 1. It can be divided by 1. Does it make sense to everybody? Should be pretty straightforward. So that's the reason. If you want to implement those kind of things in MATLAB, this is going to be 0 and 1. Even though I say this thing is not physically implementable using any hardware, but in MATLAB you can just simulate the transfer function, anything you want to. I'm not pretty sure whether MATLAB is going to give you some kind of warning message. It used to do something like that, but I don't think it is doing that right now. In 2017, I don't think it's going to give you any error message. But anyway, this is how we do that. For G, it is going to be TF 1, 1.8, and 1. Okay, then what we can do is my closed loop transfer function is going to be C multiplied by G over 1 plus C multiplied by G. This is going to be the transfer function. Sometimes this is not going to be exactly the same as what I'm writing down over here. It gives you a more complex form, but it doesn't really matter, because if you can simplify the equation, you should go back to this equation, okay? So sometimes it might give you like 6th order, 5th order, it doesn't really matter, okay? Then the next thing you can do is using step, but I don't want you guys to do step. You would do U equals to 1. T equals to 0, 0.01 to 3. What does this mean? This is going to be my time, starting from 0 seconds and end at 2 seconds. The interval is going to be 0.1 0.01 second or 100 hertz. Makes sense to everybody? Then the next thing is you want to have your input. In this case, what is my input? Unit step. So this one needs to be 1. There in MATLAB, there is a specific command you can use, which is once. 1,000. You need to have a corresponding length of this thing because the length or the components in this vector must be the same as this vector. You guys learned C programming before, right? If you want to do the simulation, the vector, input vector should be the same as your time vector. So you need to use the length of t, and it's going to be this 1,000 multiplied by 1. Does it make sense? The next thing we want to do is do y equals to LSIM. I think it's G C L U and T. I don't remember which one is first. You just use help to do LSIM. One is input, the other one is time. Okay? Then you can just plot T and Y. Then that will give you the result I have over here. Okay? Keep in mind, I don't remember whether this order is correct or not, but it should be one input and the other one is time. Any questions? If you want to have multiple things, means that if you want to have multiple KD, how are you going to deal with that? Do that multiple times, and if I ask you guys to do 10 times, then the next thing you come to my office and try to kill me. What are we going to do? You can say KD1 equals to 1. I'll just show you 2 KDs. And KD2 equals to 10. Okay? So this part is going to be C1. C2 equals to be C. EF KD2 AP. Of course, you can run the code twice, but I don't prefer to do that. It's just tedious. And GCL2 if you know how to use array, you can just use array, but here I'll just do the repeat step. And this one is going to be the same because the only thing different is what? Controller. The input and the time remains the same. You can change this one to 0.01, make it 1 kilohertz or whatever, but it will be the same. So this one over here, then this part needs to be plot T, Y1, T, Y2. So you can plot both lines in the same figure. Okay, and if you want to change the color, plot T, Y1. Let's say you want to do blue star. You can change the color, you can change the shape. T, Y2, red dash line. You just type help, plot. You can generate anything you want to. Okay, you can even change the whether it's going to be bold or how much, what is the point of Why? You can change anything. Sometimes this can be handy if you need to turn your homework or your project with those kind of things with a figure. MATLAB is a great tool to help you to generate those plots. Okay. The only thing you need to be careful is t and y must have the same number of components. You cannot say this one is 100 components and this one is 1,000. MATLAB is going to give you some error signals. Okay. Okay, so now we talk about P controller, I controller, and D controller. When we are dealing with P controller, again, AP is going to reduce steady state error. Right? Drawback is the mean ratio becomes smaller. It means that overshoot increases. Right? So that's the advantage, and this is disadvantage. When you are using I controller, since this I controller is an integration, so we're going to have 0 steady state error for unit input response. But when you are dealing with Ki, your damping ratio zeta can be decreasing when Ki is increased. And also, the overshoot can be increased. That's a drawback. Even though we can have 0 steady state error, but this is going to be the drawback. When we have D controller, damping ratio can be adjusted. My overshoot can be dropped based on how I design the whole thing. However, the disadvantage of this thing is not improper, not implementable. There's a reason when we are designing the controller, we might need to consider P, I, and D altogether, but still, there are some issues we need to take care to make everything proper and physically implementable when we are dealing with PID controller. Now it's just a brief how P is going to affect your system, how I is going to affect your system, and how D is going to affect your system. Is that clear? Everyone understand what I'm trying to do? Question? Okay, I'll pretty much cover page 10. How the PID controller is going to look like, how my steady state error is going to look like, how my settling time is going to be changed, how the overshoot is going to be changed, how the rise time is going to be changed. You just look at this into this table and think about everything. You should be able to understand what's going on based on looking at the characteristic equation in the denominator, right? Okay. Next thing we're going to talk about is something we have talked about earlier, system response. So when you are dealing with controller design, we are not dealing with things in time domain because we are taking care of everything using transfer function. So the variable we are taking care is not time, it is what? S. So when we are dealing with everything in terms of S, we are not doing something like no, we care. But in many cases, we are dealing with things like right? And at this moment, there are a few things I have emphasized all the time. They are overshoot and the settling time. Those are two things important to us. So when I say I want to have 5% overshoot, what am I talking about? 0.707 damping ratio. So if you put things over here, what does this going to look like? So this is kind of a review. You guys will need to know. So when we are dealing with this guy, this one over here must have real part and imaginary part, right? If you take this one is a quadratic equation or second order equation. If you try to find the root, what are you going to have? S equals to negative. Right? Any question? And when we have this thing over here, before I move on, let me remind you one more thing. When we are dealing with controller or transfer function, we only care about first order and second order equations. We don't care about third order or higher orders. What is the reason? You guys still remember? Because all the equations can be converted into the combination of first order and second order systems. So when you are drawing something like this, the only thing you need to worry about is second order, because the first order is only on the real axis. So the only thing we need to worry about is second order. And by looking at this thing over here, if we have our damping ratio equals to 0.707, what happened to here? This one is definitely going to be 0.707, right? What about this part?
0.707.
Right, those two becomes the same. So when they are the same, you put things over here that is going to be what is the angle? If you draw a line, those two are the same. You draw a line. 45 degrees. So this is something you will need to be careful. And I think we talked about this last time. And we have another line over here. Doesn't look like 45 degrees. Okay, so if you are within this region, whether your damping ratio is going to be greater than 0.7 or going to be smaller than 0.7 in this region and in this region, smaller or greater? Smaller? Greater? No, it's going to be smaller. What? We always talk about if the damping ratio becomes bigger and bigger and it becomes 1. When this one becomes 1, this becomes what? Real number. When it's real number, it's going to be along this side. Which means if you have smaller damping ratio, it must be this region. So over here and over here is something we less desired, because the overshoot is definitely going to be greater than 5%. 5%. Okay, so this line and this line is something critical to you. Second thing is if it's first order, we're talking about 4 over tau, right? So you must know your root somewhere over here. Then, depending on what you're going to do, you can determine what is your tau should be located. If you are having a second order system, it's the same. 4 over zeta omega n. So by knowing where this one is located, you should be able to know how fast the system is going to reach its steady state, right? So if you specify how fast your system is going to look like, then you kind of put where you want to have your zeta omega n to be located. And if you know where this one is going to be located, you should be able to find out what is the imaginary part of your system. Anything within this region is what? Too slow. Only when your system, only when your pole is on the left-hand side of this point, your system is fast enough based on your criteria. So when you are dealing with those kind of things, depending on whether it's a first order system or a second order system, you need to do 1 over tau or negative zeta omega n accordingly. The reason is because we want to have our overshoot to be specified. Second reason is I want to have my sailing time to be satisfied. And the key we're using over here is 2%. Sometimes you might say it's 3%, 5% or 1%. That is going to be taking care of that separately. The problem you guys deal with in your homework this time is what? 1%. So be sure you use the correct equation. That should be 5 over zeta omega n, right? To be exact, it should be 4.6, but if you use 5, any question? Okay, so this is how we use the S-domain plot to design our controller. In page 11, yeah, you're going to see there are something which is important. That is your what's that? Oops, I think I misplaced something. Anyway, so you're going to see the if your damping ratio becomes smaller, how big the overshoot is going to look like. Okay, let's deal with one example. Then, based on this configuration, you should be able to know where you're going to put your closed loop pole, right? Because if you put your closed loop pole over here, it is going to be too slow, and the overshoot is going to be too much. If you put this over here, it's going to be fast enough, but your overshoot is greater than desired. If you put things over here, it's too slow, but you won't generate too much overshoot. But if you put your closed loop pole over here, you're safe. Okay, so this map is going to be used in that way. 5.6. Consider the first order motor system as shown in this figure. If the desired performance needs to be 1, the overshoot is less than 5%, settling time is less than 2 seconds. Steady state error, 2-step input is 0. Design a corresponding controller. So I got okay. We are given %5 overshoot. We are given settling time. Smaller than 2 seconds. We are given steady state error equals to 0. So what do we want to find? So we have learned many things in this chapter. So by looking at the given conditions over here, can you specify something we have been discussed so far? So when we say that overshoot is less than 5%, what does that mean?
Damping ratio is
What is this one? Right? So it means that zeta omega n greater than 2. What is this one? Which type of controller you must use? So you need to have I controller. Okay. So we have specified those things. Then we're going to put everything all together. We are not going to use PID controller because PID controller is still not implementable unless it's specified. Normally we just do PI controller, and PI controller is one of the most common controller you're going to have when you are designing system. Normally we're going to use the What's P dot? This is something we're going to talk about in topic 7. This is 7. So when we are designing our controller, we are trying to have PI controller, right? So let's start to solve the problem. Before you start to solve the problem, it is important to rewrite the problem statement based on your own language, which means you will need to know what is the overshoot. What is your settling time? Do you need to have 0 steady state error? If you do, what are the conditions or what are the design criteria you need to have? Then you decide what you need to find. Because sometimes I might tell you you need to find PD controller, but I won't say that directly. I'm telling you based on the configuration. Sometimes I'm telling you, okay, I only need to have the steady state error to be less than a certain amount of maybe 10%. Then P controller is good enough. Okay? So when you are reading the problem statement, those are the things important you need to figure out before you start to solve the problem. Okay? So since I'm telling you I'm going to have PI controller, it means that I'm going to have what? KP plus KI over S. Right? Then we need to put our system all together. Let me ask you a question. This one is what? First order system. After I plug in the controller, will I have a second order or still a first order system? First order? Second order. More than second order. I don't care. Give me the credit. Give me 100 points. You're honest. Now, sometimes it can become the second order, okay? And depending on what you're going to do, you're going to have maybe third order or higher order, because when you have PID controller, chances that you might have higher order. But keep in mind, those conditions still need to be fulfilled, which means the dominant system is specified by those criteria. All the other poles must be what? 5 times faster than the sink. Then your system will be stable. Then you determine that based on this one. Okay? So, when we have something like this, my closed loop system, GC S plus 1, 2. Okay, so you're going to have 2 KPS plus I S plus 1 plus 2 KPS plus KI. What are you going to do? You are going to have S squared plus 1 plus 2 KP S plus 2 KI 2 KPS plus KI. In this problem, we do not care about the effect of 0. We just need to worry about those parts. And this is what the second order system. So what are we going to do? We just equivalent the denominator was S squared plus 2 zeta omega n S plus omega n squared. Okay? So in that case, before I move on, omega n is going to be 2, right? Zeta is going to be 0.707. You will argue with me saying that I want to have zeta equals 2.95. This one is just enough for the criterion. You want to tell me, okay, my zeta omega n I want to have is going to be 5. Then it's going to be even faster. That's fine. As long as you are having those numbers, your system are fulfilled. Okay? So if we have those kind of things all together, I'm going to have my omega n equals 2.828 radians per second. So my S squared plus 1 plus 2 kp S plus 2 ki is going to be S squared plus 4s plus 8. Ki is going to be 4. Kp is going to be 1.5. And that will be the answer. Is that straightforward? This method we call pole placement. This method is handy. However, it has a major drawback, because when we are dealing with those kind of things over here, do I consider any effect of 0? I got S, I got I over here. I got this equation over here, but I never consider that part, right? So even though pole placement can satisfy everything in terms of characteristic equation, however, this part is never considered. Sometimes this is going to be something wrong when you are designing a controller. We're going to take care of the controller design when we are talking about locus in topic 7. That is going to give you more detail how the 0 is going to affect the overall system. Okay, but at this moment, if you just need to fulfill the second order equation, damping ratio, overshoot, those kind of stuff, this part is good enough. Any question? Two more minutes. The next example, I'm not going to explain that. It's example 5.7. That example is second order equation, and you need to design a PID controller, which means this part is going to be more complex. The solution is given, the solving procedure is given, right?
Yes.
So when you can just look at those kind of things, and well, before you look at the solving procedure, please just solve everything manually. Make sure you understand everything, then check whether your answer is correct or not. Okay? Okay, we're going to have a break. Then when we come back, we're going to talk about nonlinearity of our PID controller.